April 18, 1943, 35,000 feet above Bougainville Island, 18 P-38 Lightning fighters climbed through the tropical sky on a mission that would prove the value of chemistry over engineering mythology. Captain Thomas Lanphier pushed his throttles forward, feeling the twin Allison engines respond with authority that Japanese intelligence had declared chemically impossible. Below, Admiral Isoroku Yamamoto's transport flew toward an appointment with American fuel technology that would demonstrate how wars were won not just through tactical brilliance, but through industrial chemistry that transformed petroleum sludge into liquid power. The Lightnings burned 100-octane aviation gasoline, a fuel mixture that most petroleum experts had considered too expensive for practical military use just 5 years earlier. Each gallon represented breakthrough chemistry developed by a French automotive engineer who had never formally studied petroleum refining, yet whose catalytic process would prove more decisive than any weapon system deployed in the Pacific War. The Japanese pilots protecting Yamamoto's aircraft flew Mitsubishi Zeros powered by engines burning 87-octane fuel adequate for the lightweight fighters that had dominated Pacific skies in 1941, but increasingly obsolete against American aircraft whose performance advantages traced directly to molecular innovations occurring in Pennsylvania refineries thousands of miles from combat zones. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The engagement lasted less than 20 minutes, but those minutes validated years of chemical engineering that had transformed American fighter capabilities in ways Japanese aviation never anticipated. Lanphier's Lightning, accelerating through speeds that should have been impossible at altitude with conventional fuel, intercepted Yamamoto's transport and sent it crashing into the jungle. The mission succeeded not through superior tactics alone, but through fuel chemistry that enabled American fighters to operate at power settings Japanese engineers had calculated as mechanically impossible. The story of that fuel began not in military laboratories or government research facilities, but in the Paris workshop of Eugene Houdry, a mechanical engineer whose passion for automobile racing led him toward discoveries that would reshape petroleum chemistry and alter the course of the Second World War. Born in 1892 to a wealthy French steel manufacturing family, Houdry had demonstrated mechanical aptitude from childhood. Preferring the company of engines and machinery to the social expectations of French aristocracy, his formal education in mechanical engineering at the École des Arts et Métiers provided a technical foundation, but his true education came through racing cars at speeds that pushed gasoline engines beyond their design parameters. After serving with distinction in the French Tank Corps during the Great War, earning citations for extraordinary courage under fire, Houdry returned to civilian life, determined to improve the internal combustion engines he had witnessed failing under combat conditions. His racing experiences had revealed fundamental limitations in available fuels. Engines capable of higher compression ratios and greater power output were constrained by gasoline that detonated prematurely under pressure, destroying pistons and cylinder heads through violent explosions that engineers called knocking. The petroleum industry accepted these limitations as unavoidable consequences of refining chemistry that had remained essentially unchanged since the 19th century. Houdry rejected that assumption with the obstinacy of an engineer who understood that chemical processes were no more immutable than mechanical ones. In 1922, he began experimenting with catalytic processes that could transform heavy petroleum fractions into lighter, higher quality gasoline through molecular restructuring rather than simple distillation. His initial work focused on converting coal into liquid fuel, a project that consumed years of effort and significant personal investment before yielding promising but commercially impractical results. The coal liquefaction research failed economically, but it taught Houdry critical lessons about catalytic chemistry that would prove invaluable when he redirected his attention toward petroleum refining. The conventional refining process of the 1920s and early 1930s relied on thermal cracking, heating crude oil under pressure until large hydrocarbon molecules broke apart into smaller ones, suitable for gasoline. This method was inefficient, producing gasoline with octane ratings between 40 and 70, adequate for low-compression automobile engines, but increasingly inadequate as engine designers sought higher power output through increased compression ratios. Thermal cracking also generated large quantities of unusable residue, waste products that represented lost economic value and squandered petroleum resources. Houdry envisioned a process using solid catalysts to break petroleum molecules selectively, producing higher proportions of desirable compounds while minimizing waste. He experimented with various catalyst materials, testing clays, silicates, and aluminum compounds under different temperature and pressure conditions. His laboratory in France became a maze of experimental equipment, operating at the intersection of chemistry and mechanical engineering, combining Houdry's formal training with his intuitive understanding of how molecular behavior could be channeled through proper catalyst selection and reactor design. By 1930, Houdry had achieved laboratory-scale success, producing gasoline with octane ratings approaching 90 through catalytic cracking, but translating laboratory results into industrial-scale production required capital investment and petroleum industry expertise that France could not provide during the economic depression strangling global commerce. American petroleum companies, however, recognized potential advantages in any process that could increase gasoline yield from crude oil while improving quality. The Vacuum Oil Company invited Houdry to demonstrate his process in the United States, leading to his immigration in 1931 and beginning a partnership that would eventually attract Sun Oil Company's attention. Sun Oil, a Philadelphia-based refinery operation, possessed both the financial resources and entrepreneurial spirit necessary for developing Houdry's radical approach to petroleum refining. Company executives understood that aviation represented a growing market for high-quality gasoline, particularly as military aircraft development accelerated in response to European tensions. Arthur Pugh, Sun Oil's research director, recognized that Houdry's catalytic process could produce aviation gasoline with octane ratings exceeding anything available through thermal cracking. In 1933, Sun Oil committed to funding development of an industrial-scale catalytic cracking unit based on Houdry's principles. The engineering challenges were immense. Houdry's process required moving petroleum vapor through beds of solid catalyst maintained at precise temperatures exceeding 1,000 degrees Fahrenheit. The catalyst gradually accumulated carbon deposits that reduced effectiveness, requiring periodic regeneration through controlled burning that restored catalytic activity. Designing equipment that could handle these thermal cycles repeatedly without mechanical failure pushed 1930s metallurgy to its limits. Houdry worked 16-hour days, supervising construction of experimental reactors, modifying designs when thermal stresses cracked steel containment vessels, adjusting catalyst formulations when regeneration cycles proved too aggressive or insufficient. By 1936, Sun Oil operated a pilot plant, demonstrating that catalytic cracking could produce gasoline with octane ratings consistently above 90. The economic advantages were compelling. Houdry's process converted 45% of crude oil into high-quality gasoline, compared to 25% through thermal cracking, effectively doubling usable yield from each barrel of petroleum. The higher octane gasoline commanded premium prices from aviation customers whose engine performance depended on fuel quality, but the capital costs of constructing catalytic cracking units exceeded anything petroleum companies had previously invested in refining technology. The first commercial-scale Houdry unit began operation at Sun Oil's Marcus Hook refinery in Pennsylvania during June 1937. The facility represented an engineering achievement that bordered on industrial sculpture, a complex arrangement of reactors, regenerators, and vapor transfer systems operating in precisely timed cycles. Petroleum vapor flowed through catalyst beds for exactly 3 minutes before switching to regeneration mode, a ballet of valves and temperature controls that required constant monitoring and adjustment. When operating properly, the unit produced aviation gasoline testing at 100 octane, a rating that petroleum chemists had considered unattainable through conventional refining just 5 years earlier. The military implications became apparent immediately. Aircraft engines using 100-octane fuel could operate at higher compression ratios, generating significantly more horsepower from the same displacement. Alternatively, engines could maintain standard power output while consuming less fuel, extending range and endurance. For military aviation, where performance margins often determined combat outcomes, these advantages justified the higher cost of catalytic cracking. In 1937, the United States Army Air Corps mandated 100-octane fuel for all combat aircraft, a specification that seemed impossibly demanding until Houdry's process made commercial production feasible. The Royal Air Force, observing American aviation fuel developments with keen interest, recognized that 100-octane gasoline could transform their fighter capabilities as war with Germany appeared increasingly inevitable. British fighters in 1939 used 87-octane fuel, adequate for the Rolls-Royce Merlin engines powering Hurricanes and Spitfires, but limiting maximum power output and combat performance. Switching to 100-octane would increase engine output by approximately 20%, providing British fighters with performance margins that might prove decisive in aerial combat. But Britain possessed no facilities for producing high-octane aviation fuel in the quantities modern warfare would demand. American petroleum companies, led by Sun Oil and Standard Oil of New Jersey, began constructing additional catalytic cracking units throughout 1938 and 1939. The investment was extraordinary, each unit costing several $million and requiring months of construction and commissioning. By the time Germany invaded Poland in September 1939, American refineries could produce approximately 40,000 barrels per day of 100-octane aviation gasoline, a supply sufficient for United States military requirements, but far short of what Britain would need if drawn into European war. The technical and economic feasibility of scaling production to meet Allied combat demands remained uncertain as the world descended into conflict that would test every assumption about industrial capacity and chemical engineering. The Japanese Navy, developing the Mitsubishi Zero fighter during the late 1930s, designed an aircraft optimized for the 87-octane fuel Japanese refineries produced through conventional thermal cracking. The Zero achieved remarkable performance through radical weight reduction and aerodynamic efficiency rather than engine power, with empty weight under 4,000 pounds and wing loading of just 25 pounds per square foot. The Zero could outmaneuver heavier fighters and operate from limited airfield facilities throughout the Pacific. Japanese designers accepted the compromises this approach required, including minimal armor protection, no self-sealing fuel tanks, and vulnerability to battle damage that more robust aircraft could withstand. The Zero represented one philosophy of fighter design, maximizing agility and range through structural efficiency while accepting reduced survivability. American fighter development followed different principles, emphasizing pilot protection, firepower, and performance advantages through superior engine power. The Lockheed P-38 Lightning, entering development in 1937, embodied this approach through twin-engine configuration that provided redundancy, substantial firepower concentrated in the nose, and performance capabilities that required 100-octane fuel to realize their full potential. The Lightning's twin Allison V1710 engines, each displacing 1,700 cubic inches and producing over 1,000 horsepower, represented American confidence in fuel chemistry that could support high compression ratios and sustained high-power operation. The contrast between Japanese and American fighter philosophy would prove decisive in Pacific combat. But that decision reflected industrial capacity and chemical engineering as much as design brilliance. Japan's petroleum industry, constrained by limited crude oil supplies and outdated refining technology, could not produce high-octane aviation fuel in meaningful quantities. Japanese fighters would fight the entire war using 87-octane gasoline, accepting performance limitations that Allied fuel chemistry had already overcome. American fighters would burn 100-octane fuel as standard issue, with higher grades of 130 and 150 octane available for specific applications. This chemical advantage, invisible to observers watching aircraft in flight, would prove as significant as any tactical innovation or pilot training program in determining Pacific Air War outcomes. The Battle of Britain in 1940 demonstrated high-octane fuel's impact on aerial combat with clarity that convinced skeptics throughout the aviation industry. Royal Air Force fighters equipped with 100-octane fuel shipped from American refineries beginning in May 1940 suddenly possessed performance advantages over Luftwaffe aircraft that German intelligence could not explain. Spitfires and Hurricanes that had struggled against Messerschmitt. Bf-109s, during operations over France, became dominant when fueled with Houdry's catalytic cracking products. The speed increase of 25 to 30 miles per hour at low and medium altitude transformed tactical possibilities, allowing British fighters to intercept German bombers more effectively and engage enemy fighters on favorable terms. German petroleum chemists, analyzing captured fuel samples, discovered octane ratings their instruments could barely measure. Luftwaffe aircraft burned C3-grade fuel testing at approximately 87 octane, considered adequate by German standards, but suddenly revealed as inferior when British fighters demonstrated performance that conventional fuel chemistry suggested was impossible. German refineries attempted to replicate Allied fuel technology, but lacked both the catalytic cracking equipment and the industrial capacity to produce high-octane fuel in combat-relevant quantities. Throughout the war, German aviation would remain constrained by fuel chemistry limitations that reflected broader industrial inadequacies compared to American and British petroleum engineering. The strategic implications became undeniable as 1941 brought the United States into global conflict. American petroleum companies, recognizing that military fuel demands would far exceed peacetime production capacity, accelerated construction of catalytic cracking units throughout the country. Shell Oil, Standard Oil, and smaller refineries licensed Houdry's patents and built facilities based on his engineering principles. By December 1941, American refineries could produce 120,000 barrels per day of 100-octane aviation gasoline, triple the capacity available just 2 years earlier. But even this dramatic expansion would prove insufficient for the aerial warfare that Pacific and European operations would demand. The Doolittle raid of April 1942, though tactically limited, demonstrated both the capabilities and limitations of American aviation fuel supply. The 16 B-25 bombers launching from USS Hornet burned 100-octane gasoline, enabling them to carry maximum bomb loads and fuel for the one-way mission to China. But the raid's planning had been constrained by fuel availability considerations that revealed how petroleum chemistry influenced strategic options. Every gallon of high-octane fuel allocated to the Doolittle mission represented gallons unavailable for training, transport operations, or defensive patrols. The raid succeeded brilliantly in demonstrating American resolve, but it also illustrated how fuel production capacity shaped military planning as much as aircraft availability or pilot training. The P-38 Lightning began arriving in the Pacific Theater during August 1942. Its twin-engine configuration immediately appreciated for the safety margin it provided over vast oceanic distances where single-engine failure meant certain death. The Lightning's Allison engines, each producing 1,325 horsepower in the G model, required 100-octane fuel to deliver their rated performance. Operating on lower-grade fuel would cause detonation that could destroy engines within minutes of high-power operation. This fuel dependency meant that P-38 operations were constrained not just by aircraft availability or maintenance capacity, but by fuel logistics that required shipping thousands of gallons of specialized gasoline across thousands of miles of ocean to forward airfields throughout the Pacific. The Zero fighters that P-38s encountered over Guadalcanal, New Guinea, and throughout the Solomon Islands represented Japanese aviation philosophy optimized for different fuel chemistry. Mitsubishi's Sakai radial engines produced approximately 1,100 horsepower from 14 cylinders, displacing 46 liters, respectable output from engines designed for 87-octane fuel. But the compression ratios and thermal stresses these engines could withstand were fundamentally limited by the fuel chemistry Japanese refineries could provide. Japanese engineers understood that higher octane fuel would enable more powerful engines, but their petroleum industry lacked the catalytic cracking technology necessary for producing such fuel economically. The result was aerial combat, where chemistry conferred advantages that tactics and pilot skill could mitigate but not overcome. P-38 pilots learned to avoid turning dogfights where the Zero's superior agility provided advantages, instead using speed and altitude capabilities enabled by superior fuel chemistry to dictate engagement terms. The Lightning could cruise at speeds above 350 miles per hour, accelerate rapidly during power dives, and climb at rates exceeding 4,000 feet per minute, performance margins that reflected the 100-octane fuel flowing through its Allison engines. Zero pilots, constrained by fuel chemistry that limited their engines to lower compression ratios and reduced power output, found themselves increasingly relegated to defensive tactics as American fighters exploited every advantage their fuel technology provided. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The human dimension of fuel chemistry advantages became personal for pilots like Major Richard Bong, who achieved 40 confirmed victories, flying P-38s over the Pacific. Bong's success reflected exceptional gunnery and tactical skill, but it also depended on fuel chemistry that enabled his Lightning to outperform Japanese fighters in energy tactics that American pilots had developed specifically to exploit their aircraft strengths. Bong could climb above Japanese formations, dive at high speed to attack, then zoom back to altitude using excess power that his engines could sustain. Because the fuel burning in their cylinders resisted detonation at compression ratios Japanese engines could never match, his victories represented the convergence of pilot excellence and industrial chemistry, neither sufficient alone, but devastating in combination. The logistics of supplying 100-octane fuel throughout the Pacific created challenges that matched any faced by ammunition or spare parts distribution. Each gallon weighed approximately 6 pounds, and forward airfields required thousands of gallons daily to maintain fighter operations. Tanker ships carried fuel from West Coast refineries to major bases at Pearl Harbor, Australia, and New Caledonia, where smaller vessels and eventually pipelines distributed it to combat zones. The entire supply chain depended on refinery capacity that traced directly to Houdry's catalytic cracking innovations, linking Pennsylvania petroleum chemistry to aerial combat over Rabaul and Bougainville. Through industrial processes that transformed crude oil into liquid tactical advantage. Japanese attempts to develop high-octane fuel production capability failed repeatedly throughout the war. Engineers at Japanese petroleum facilities understood the theoretical basis for catalytic cracking, but implementing industrial-scale processes required equipment, materials, and expertise that Japan's war economy could not provide. Experimental facilities produced small quantities of higher-octane fuel at costs that made widespread use impossible. Japanese military aviation would fight the entire war using 87-octane gasoline, accepting performance compromises that became increasingly catastrophic as American fighters evolved through successive variants optimized for the fuel chemistry advantages Allied industrial capacity could sustain. The P-38L model, introduced in mid-1944, represented the Lightning's evolution into an aircraft whose capabilities would have been impossible without advanced fuel chemistry. The L variants, Allison V-17, 10-111 and 113 engines produced 1,600 horsepower, each using 130-octane fuel power output that required compression ratios and thermal stresses far beyond what 87-octane chemistry could support. Top speed exceeded 414 miles per hour at altitude, climb rate approached 5,000 feet per minute, and range with external tanks reached over 2,000 miles. These specifications reflected not just aeronautical engineering excellence, but petroleum chemistry that had transformed crude oil into fuel capable of supporting combustion pressures exceeding 1,000 pounds per square inch without premature detonation. The contrast with Japanese fighter development revealed how fuel chemistry constrained aircraft evolution regardless of engineering capability. The Mitsubishi A6M50 variant, introduced during the same period as the P-38L, represented incremental refinement of the original design rather than revolutionary improvement. Japanese engineers could not significantly increase engine power without higher octane fuel, and their petroleum industry could not produce such fuel without catalytic cracking technology and industrial infrastructure that Japan lacked. The A6M5 achieved modest speed increases through aerodynamic refinement and minor engine modifications, but its fundamental performance remained limited by fuel chemistry that had changed little since the war's beginning. The impact extended beyond individual aircraft performance to shape operational planning and strategic possibilities. American fighters could escort bombers on missions exceeding 1,000 miles, confident that their fuel would support sustained high-power operation throughout extended combat. Japanese fighters defending against these raids were constrained by fuel that limited both their operational radius and their combat performance at altitude, where thin air made detonation more likely. The result was systematic destruction of Japanese air power through attrition that reflected industrial capacity as much as tactical superiority. Eugene Houdry, working throughout the war to improve catalytic cracking efficiency and increase production capacity, understood that his peacetime research into automobile racing fuels had contributed to military victory in ways he had never anticipated. His innovations had doubled gasoline yield from crude oil while simultaneously improving quality to levels that made modern high-performance aviation possible. The catalytic cracking units operating throughout American refineries represented practical application of chemistry he had pioneered during years of laboratory experimentation in France, translated through American industrial capacity into fuel production that supplied Allied air forces worldwide. The statistics of fuel production revealed the magnitude of the American petroleum industry's contribution to Allied victory. By 1945, catalytic cracking units throughout the United States produced over 300,000 barrels per day of 100-octane or higher aviation gasoline. This production capacity had required investment exceeding $1 billion in 1940s currency, equivalent to 10 times that amount in modern terms. But the tactical advantages provided by this fuel made the investment economically efficient when measured against alternative costs of achieving air superiority through aircraft numbers alone, or accepting higher combat losses from performance-disadvantaged fighters. The human cost of fuel chemistry advantages was measured in pilots who returned home to families instead of becoming casualties of combat, where performance margins meant survival. P-38 squadrons, equipped with 100-octane fuel, experienced loss rates below 5% per month during 1944 Pacific operations, compared to over 15% monthly losses for units flying obsolescent aircraft or operating under fuel supply constraints. These statistics translated directly into thousands of young men who lived because industrial chemistry had provided their aircraft with performance advantages sufficient to overcome enemy numbers and tactical position. The Pacific War's conclusion in August 1945 brought retrospective analysis of factors contributing to Allied victory. Military historians focused on strategy, tactics, and industrial production capacity, but petroleum engineers understood that fuel chemistry had provided enabling advantages without which American aircraft could never have achieved the performance necessary for air superiority. Eugene Houdry's catalytic cracking process had transformed petroleum refining as completely as any technological innovation of the 20th century, with effects extending far beyond military aviation to reshape automotive transportation, commercial aviation, and petrochemical industries for generations following the war's end. The legacy of wartime fuel chemistry innovation influenced Cold War aviation development and eventually space exploration programs. The principles Houdry pioneered, using catalysts to restructure petroleum molecules into desired compounds, led directly to developments in synthetic fuels, rocket propellants, and advanced lubricants. His work established American leadership in petroleum chemistry that persisted through decades of technological competition, ensuring that advantages gained through wartime innovation continued shaping global energy industries long after immediate military requirements had passed. The P-38 Lightning, flying its final combat missions during summer 1945, represented the convergence of aeronautical engineering and fuel chemistry that had transformed aerial warfare. The aircraft's distinctive twin-boom design made it instantly recognizable, but its true revolutionary characteristic was invisible to observers. The 100-octane fuel flowing through its Allison engines embodied Eugene Houdry's understanding that petroleum chemistry could be revolutionized through catalytic processes, transforming molecular structure to produce fuels capable of supporting combustion that conventional refining methods could never achieve. That invisible advantage, developed in Pennsylvania laboratories and proven over Pacific battlefields, demonstrated how wars were won through scientific innovation as much as through courage and tactical excellence. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The transformation of aerial warfare through fuel chemistry became most apparent in combat statistics that revealed systematic Japanese aviation decline throughout 1944 and 45. American fighter pilots flying aircraft whose performance advantages traced directly to superior fuel technology achieved kill ratios exceeding 10-1 against Japanese opponents during the war's final 18 months. These numbers reflected not just pilot training or tactical doctrine, but fundamental performance margins that fuel chemistry had established. Every engagement demonstrated how petroleum engineering in Pennsylvania refineries influenced combat outcomes over Leyte Gulf, Iwo Jima, and Okinawa through invisible advantages that Japanese aviation could neither replicate nor effectively counter. Major Thomas Maguire, second only to Richard Bong in Pacific aerial victories, described the P-38's capabilities in combat reports that inadvertently documented fuel chemistry's tactical impact. Maguire's Lightning could maintain combat power at altitudes exceeding 35,000 feet, where Japanese fighters struggled to generate sufficient thrust for effective maneuvering. The Allison engines, burning 130-octane fuel at compression ratios exceeding 7-1, delivered consistent power output in atmospheric conditions that would have caused detonation and catastrophic failure with conventional gasoline. Maguire's 38 confirmed victories represented exceptional skill combined with technological advantages that petroleum chemistry had made possible. The industrial infrastructure supporting Pacific fuel logistics expanded throughout the war into a supply network whose complexity rivaled any military undertaking of the conflict. Refineries along the Gulf Coast and California processed crude oil through catalytic cracking units that operated continuously, producing aviation fuel that tankers carried across ocean routes protected by naval forces whose aircraft also depended on that same fuel. At forward bases throughout the Pacific, fuel storage facilities held hundreds of thousands of gallons in tanks that were themselves targets for Japanese attacks, recognizing how completely American air power depended on uninterrupted fuel supply. The entire system represented industrial integration on scales that peacetime commerce had never attempted, linking petroleum extraction, refining, transportation, and combat operations through supply chains measured in thousands of miles and millions of gallons. The cost of this fuel production revealed both American industrial capacity and the economic calculations that made high-octane gasoline practical for military operations, despite expenses that would have been prohibitive under peacetime conditions. Each gallon of 130-octane fuel cost approximately $3 in 1945 currency, over 30 times the price of standard automotive gasoline. A single P-38 combat mission consumed 200 gallons or more, representing fuel costs exceeding $600 per sortie before accounting for ammunition, maintenance, or pilot training expenses. But these costs were measured against alternatives, including accepting higher aircraft losses, reduced mission effectiveness, or strategic limitations that would have prolonged the war and increased total casualties. The economic efficiency of high-octane fuel became apparent when calculating lives saved and objectives achieved per dollar invested. Japanese petroleum engineers, desperate to overcome fuel quality limitations that were crippling their aviation capabilities, attempted numerous alternative approaches to increasing octane ratings without catalytic cracking infrastructure. Experiments with alcohol additives, benzene blending, and exotic chemical compounds produced laboratory results that seemed promising but failed when scaled to industrial production. Some Japanese facilities achieved octane ratings approaching 92 through extensive refining and selective blending, but production volumes were negligible compared to combat requirements. By mid-1944, Japanese aviation fuel shortages had become as critical as aircraft production problems, with high-quality fuel reserves so depleted that training flights were curtailed to conserve supplies for combat operations. The strategic bombing campaign against Japanese oil refineries and storage facilities, intensifying throughout 1945, targeted infrastructure that was already inadequate for supporting sustained military operations. American B-29s, escorted by P-51 Mustangs and P-47 Thunderbolts burning high-octane fuel, destroyed petroleum facilities that could not be rebuilt or relocated due to material shortages and industrial bottlenecks. Each successful raid reduced Japanese fuel production capacity that had never approached levels necessary for effective defense, creating a downward spiral where inadequate fuel supplies limited fighter operations that might have protected remaining refineries from destruction. The human stories emerging from this industrial warfare revealed how petroleum chemistry influenced individual fates throughout Pacific combat zones. Lieutenant Colonel Charles McDonald, commanding a P-38 fighter group during the Philippines campaign, described missions where American fighters operated at power settings that would have been suicide with inferior fuel. McDonald's pilots pushed their throttles to war emergency power during intercepts, confident that the fuel flowing through their engines would resist detonation at manifold pressures exceeding 70 inches of mercury.